Every planet in our solar system rotates. This is expected, a consequence of the angular momentum of the rotating disk of gas and dust from which they formed 4.6 billion years ago. The disk rotated in a specific direction. The planets that condensed within it inherited that rotation. They should all spin in the same direction. Most of them do. Venus does not. From a perspective looking down at the solar system from above its north pole, the perspective from which the planets orbit the Sun counterclockwise, most planets also rotate counterclockwise when viewed from that same direction. Earth, Mars, Jupiter, Saturn, Neptune. Their north poles point generally upward in this perspective, and their surfaces move from west to east under any observer. Venus rotates clockwise in this view. Its surface moves from east to west. The Sun rises in the west and sets in the east on Venus, the opposite of Earth. This is called retrograde rotation, and it places Venus in a very small category of solar system objects that spin in the opposite direction from their orbital motion. The question of why is one of the oldest open questions in planetary science, and the answer, which remains incompletely settled, touches on some of the most fundamental processes in the formation and evolution of planetary systems. On the role of chaos in the early solar system, on the nature of planetary tides, on the question of how the initial conditions of a planetary system are preserved or erased over billions of years. Tonight we are going to follow this question honestly. Not just the simple fact that Venus spins backwards, but what that fact means, how we think it happened, why it still matters, and what it tells us about the solar system and about our assumptions regarding how planets should behave. If the night is long, stay. Venus is one of the brightest objects in the sky and one of the least understood planets in the solar system. Its retrograde rotation is only the beginning of how strange it is. Let us start with the basic facts of Venus's rotation as we know them from observations. Venus has a rotational period of approximately 243.025 Earth days. This is the sidereal rotation period, the time it takes Venus to complete one full rotation relative to the distant stars. This is longer than Venus's orbital period around the Sun, which is about 224.7 Earth days. Let that sink in for a moment. Venus takes longer to rotate once on its axis than it takes to complete one orbit around the Sun. The Venusian day, in the sense of one full rotation, is longer than the Venusian year. This already makes Venus unusual. No other planet in our solar system has a day longer than its year. Mercury comes close. Its rotational period is 58.6 Earth days, and its orbital period is 88 days, so Mercury's day is about 2/3 of its year. But Venus is the only planet where the rotational period exceeds the orbital period. The solar day on Venus, the time from one sunrise to the next, which depends on the combination of rotation and orbital motion, is approximately 116.75 Earth days. Because Venus rotates retrograde relative to its orbital motion, the solar day is shorter than the sidereal rotational period. The retrograde rotation and the orbital motion partially cancel each other from the perspective of someone on Venus's surface watching the Sun. 116.75 Earth days between sunrises. About 58 Earth days of daylight, followed by 58 Earth days of darkness. At a solar flux about 1.9 times Earth's on the day side, with a surface temperature of about 465 degrees Celsius, that barely changes between day and night because the thick atmosphere distributes heat efficiently. The axial tilt of Venus is approximately 177.3 degrees. This is nearly 180 degrees, almost perfectly inverted. Another way to describe Venus's rotation, instead of saying it rotates retrograde with a small axial tilt, You can equivalently say it rotates in the same direction as other planets, but with its axis flipped nearly upside down. The north pole of Venus, defined by the right-hand rule of its rotation, points south relative to the ecliptic plane. Both descriptions are mathematically equivalent. Both say the same thing: Venus spins the wrong way. The question is why. Let us talk about what we know about how planets get their rotation in the first place, because understanding the baseline makes the anomaly of Venus clearer. As we discussed in the context of why everything spins, the solar system formed from a rotating molecular cloud. The collapse of this cloud, conserving angular momentum, created a disk. The disk rotated in a specific direction, which became the orbital direction of all the planets. Planetesimals, the small rocky bodies from which the planets accreted, formed within this disk and inherited both the orbital direction and a general tendency toward prograde rotation. As planetesimals collided and accreted to form larger bodies, the random contributions of angular momentum from many smaller collisions tended to produce a net rotation in the same direction as the disk, prograde rotation. This is why most planets spin in the same direction as they orbit. It is a statistical tendency from the accretion process. Any individual collision could add or subtract angular momentum in any direction, but the average of many collisions during the accretion phase tends to produce prograde rotation simply because the orbiting material that was most available for accretion was itself moving prograde. The axial tilt of any individual planet, how far its rotation axis is tilted relative to its orbital plane, depends on the specific history of large impacts late in the accretion process. Large impacts between roughly formed planet-sized bodies can dramatically change the rotation state. Earth's 23.5-degree axial tilt is thought to result from the giant impact that formed the Moon, approximately 4.5 billion years ago. Uranus's extraordinary 98-degree tilt is thought to result from one or more major collisions in the early solar system. The range of axial tilts we see in the solar system, from near zero for Jupiter at 3 degrees to extreme for Uranus at 98 degrees, reflects this random final bombardment. Each planet has its own specific collision history, and that history left its mark on the rotation state. Venus's near 180-degree inverted axis, or equivalently its retrograde rotation, is in this context one of the most extreme outcomes possible. Something pushed it to nearly a complete flip. What was that something? Let us talk about the main hypotheses that have been proposed over the decades, because this is a question where the answer is still being worked out and the scientific community has not fully converged. Hypothesis 1. A large impact flipped Venus. This is the most straightforward hypothesis and in some sense the most intuitive. If a giant impact can tilt Uranus to 98 degrees, why not tilt Venus to 177 degrees? A sufficiently large and favorably directed impactor could flip the rotation axis of a planet. The problem with this hypothesis is that it requires a very specific type of impact, one that adds angular momentum in precisely the anti-prograde direction. Large impacts are stochastic; they can produce any outcome. But the specific outcome of near-perfect inversion requires a coincidence of timing, mass, and direction that is possible but not obviously likely. More importantly, there is no other obvious evidence that Venus experienced such an extreme impact. The Moon is strong evidence for Earth's giant impact, a large iron-poor body that accreted from ejected material. Venus has no large moon. There is no smoking gun of a catastrophic collision in Venus's observable characteristics. This does not rule out the impact hypothesis. The absence of a moon could result from many other factors, but it weakens the simplest version of the story. Hypothesis 2. Tidal effects flipped Venus over time. Venus experiences tidal forces from the Sun, gravitational forces that vary across the diameter of the planet, creating a torque on its rotation. The Sun's tidal influence on Venus is significant because Venus orbits closer to the Sun than Earth, and the tidal force scales as the inverse cube of distance. The idea here is that over billions of years, solar tidal torques could have slowed Venus's initial prograde rotation to zero and then reversed it into retrograde. This is the same mechanism by which our Moon became tidally locked to Earth, tidal dissipation of rotational energy, but operating over longer timescales and without achieving the synchronization endpoint. This hypothesis has been studied extensively. The challenge is that the solar tidal torque alone, acting on a rigid planet, would tend to drive Venus towards synchronous rotation rather than toward retrograde. The direction of tidal forcing pushes toward the equilibrium where the rotation rate matches the orbital period in prograde direction. To end up retrograde requires something more. One elegant modification involves the atmosphere. Venus has an extraordinarily massive atmosphere, surface pressure about 92 times Earth's, dominated by carbon dioxide. This thick atmosphere has its own tidal dynamics. The Sun heats it, creating atmospheric pressure waves that travel around the planet. These atmospheric tides exert their own torque on the solid planet beneath. The atmospheric thermal tide tends to push Venus's rotation in the retrograde direction, opposite to the solar gravitational tide, which tends toward prograde. The competition between these two tidal effects could, in principle, explain Venus's current rotation state as an equilibrium between atmospheric and gravitational tides. This atmospheric tidal hypothesis was developed theoretically and has considerable support. Simulations show that the balance between solar gravitational tides and atmospheric thermal tides can produce a retrograde equilibrium rotation at a rate similar to what Venus actually has. But this hypothesis faces its own challenges. It requires the atmospheric tidal torque to be precisely strong enough to counteract the gravitational tidal torque. Whether Venus's actual atmosphere produces exactly the right torque depends on poorly constrained parameters about how atmospheric energy is dissipated. Hypothesis 3. Venus's early rotation was already retrograde or very slow. This hypothesis proposes that the initial conditions during Venus's formation were simply different from those of Earth or Mars, that through a particular history of large impacts during the late stages of accretion, Venus ended up in a rotation state that was already retrograde or nearly zero before any subsequent tidal evolution. In this view, the current retrograde rotation is essentially a fossil of the formation process, a consequence of the specific sequence of large impacts that happened to hit Venus late in its accretion rather than an ongoing tidal evolution result. This is a somewhat less satisfying explanation in that it essentially says the anomaly is just a coincidence of formation history. But coincidences happen. The solar system contains planets across a wide range of rotation states, from Jupiter's near vertical axis to Uranus's near horizontal, and some of that range is just the result of the random statistics of large late impacts. Hypothesis 4. A combination of processes. The most likely explanation may involve several of these mechanisms operating over different timescales. Venus may have started with a prograde rotation that was already unusual, perhaps a slow prograde rotation due to particular formation history. Solar gravitational tides and atmospheric thermal tides then operated over billions of years to bring the rotation to its current state. Perhaps a large impact early in the planet's history set the initial conditions for this subsequent evolution. Disentangling these contributions is extremely difficult because we cannot directly observe Venus's rotation state in the distant past. All we know is the current state. The processes we invoke to explain it must be inferred from physical models. Let us now talk about the specific measurement history of Venus's rotation, because the story of how we actually determined that Venus rotates retrograde is itself interesting. Venus is completely covered in clouds. Permanent global cloud cover composed primarily of sulfuric acid droplets extending from roughly 45 to 70 kilometers altitude. These clouds are completely opaque to visible light. From Earth, using optical telescopes, you can never see Venus's surface. This means that for most of the history of astronomy, the rotation period of Venus was unknown. No surface features were visible. Spectroscopic methods sensitive to the Doppler shift of light from approaching and receding limbs gave conflicting results. Different observers reported different values, ranging from a Venusian day lasting about 24 hours, similar to Earth's, to much longer periods. The breakthrough came with radar. In 1962 and 1963, Jodrell Bank Observatory in the UK and several American radio astronomy facilities bounced radar signals off the surface of Venus. Radar penetrates clouds. The return signals showed a Doppler shift pattern consistent with a retrograde rotation with a long period. This was the first confirmation that Venus rotates retrograde. The scientific community initially met the result with some skepticism. It was so unexpected. But subsequent radar measurements consistently confirmed it. The Magellan mission, a NASA spacecraft that orbited Venus from 1990 to 1994, used synthetic aperture radar to map the entire surface of Venus with high resolution. By tracking the positions of surface features over the mission duration, Magellan precisely determined the rotation period and the direction of rotation, confirming and refining the ground-based radar measurements. The current best value for Venus's sidereal rotation period, 243.025 Earth days retrograde, comes from combining decades of radar observations and spacecraft tracking data. Let us now talk about how the retrograde rotation of Venus connects to its other extreme characteristics. Because Venus is strange in multiple ways, and the rotation is one of several interconnected anomalies. Venus is approximately Earth's twin in terms of size and mass. Its diameter is about 95% of Earth's. Its mass is about 81.5% of Earth's. Its density and bulk composition are similar. By these measures, size, mass, composition, Venus and Earth are the most similar pair of planets in the solar system. And yet Venus is profoundly different from Earth in almost every way that matters for habitability. Surface temperature, approximately 465 degrees Celsius, hotter than Mercury despite Venus being farther from the Sun, hot enough to melt lead. Hot enough that spacecraft on Venus's surface have survived only about an hour before being destroyed. Surface pressure, 92 times Earth's atmospheric pressure, equivalent to being 900 meters deep in Earth's oceans. Atmosphere composition, approximately 96.5% carbon dioxide, 3.5% nitrogen, with trace amounts of sulfur dioxide, water vapor, argon, and other gases. The thick CO2 atmosphere drives a runaway greenhouse effect that is responsible for the extreme surface temperatures. Cloud composition, sulfuric acid droplets. The clouds that obscure the surface reflect about 75% of incoming sunlight, making Venus the most reflective planet in the solar system and the brightest object in the night sky after the Moon. But the 25% of sunlight that gets through is trapped by the greenhouse gases with extraordinary efficiency. No magnetic field. Unlike Earth, whose molten iron outer core generates a planetary magnetic field that deflects the solar wind, Venus has essentially no intrinsic magnetic field. Why Venus lacks a magnetic field, despite its similar size and composition to Earth, is itself an open question. No moons. Despite being similar in mass to Earth, which has a relatively large moon, Venus has no natural satellites. No evidence of plate tectonics in the same form as Earth's. Venus appears to have a geologically active surface. Evidence of past volcanism is abundant, and some possible evidence of current or recent volcanic activity has been reported. But the global tectonic style appears different from Earth's mobile lid tectonics. How does the retrograde rotation connect to these other anomalies? The lack of a magnetic field may be related to the rotation. Earth's magnetic field is generated by the geodynamo, convection of liquid iron in the outer core, driven in part by the Coriolis effect from Earth's rotation. A rapidly rotating planet tends to produce organized convective flows that efficiently generate a magnetic field. A very slowly rotating planet, like Venus with its 243-day sidereal period, may have less efficient dynamo action regardless of the state of the core. Whether this is actually the reason Venus has no magnetic field is uncertain. The details of planetary dynamos are complex and depend on many factors beyond rotation rate, but the connection is plausible. The lack of a moon is possibly connected to Venus's formation history and the same processes that produced its unusual rotation. If Venus experienced a large late impact that affected its rotation, the properties of that impact might also have prevented the formation of a bound moon or caused an existing moon to be lost. This is speculative. The absence of plate tectonics in the Earth-like form may be connected to the lack of water. Earth's plate tectonics are facilitated by the presence of water, which lubricates fault zones and reduces the viscosity of subductive material. If Venus's water was lost early, through a runaway greenhouse effect driven by its proximity to the Sun, the loss of water could have led to the cessation or prevention of Earth-like plate tectonics. The chain of cause and effect connecting these anomalies is uncertain, but they are connected, all products of Venus's history, all potentially influenced by the same early events that produced the retrograde rotation. Let us now talk about what Venus's surface actually looks like, because the radar imaging from Magellan has given us a detailed picture of a world that is visible from Earth every few months as the brightest object in the night sky, but whose surface has been seen only through radar. Venus's surface is dominated by vast volcanic plains, lowland regions covered with lava flows. These plains cover roughly 80% of the planet's surface. The lavas are generally basaltic, similar in composition to oceanic basalts on Earth, consistent with Venus being a geologically active, rocky planet. Scattered across the plains are volcanic edifices. Mart Mons, the highest volcano on Venus, at about 8 kilometers above the mean surface radius, is a large shield volcano, similar in form to Hawaiian shields on Earth. Hundreds of other volcanic constructs of various sizes are distributed across the surface. Venus also has highland regions, elevated continental-scale platforms. Ishtar Terra in the north contains the Maxwell Montes, Venus's highest mountain range, at about 11 kilometers above the mean surface radius, higher than Earth's Everest above sea level by a couple of kilometers. The surface shows relatively few impact craters, about 1,000 total across the entire planet. This is remarkably few for a body of Venus's size. Earth's moon, with a similar surface area, has hundreds of thousands of craters. The explanation appears to be that Venus's surface is geologically young. Resurface events have erased older craters. The surface age is estimated at roughly 300 to 600 million years. Venus appears to have undergone a global resurfacing event in its geological past that reset the crater count. What caused this resurfacing is debated. One model, catastrophic resurfacing, proposes that Venus episodically undergoes global volcanic upheavals that completely resurface the planet, followed by long, quiet periods. Another model, gradual resurfacing, proposes a more continuous geological evolution, with different resurfacing rates in different locations. In 2023, analysis of Magellan radar data by a team led by Robert Herrick at the University of Alaska Fairbanks found direct evidence of a vent on Mart Mons that changed between observations in 1991, indicating volcanic activity during the Magellan mission. This was the first direct evidence of active volcanism on Venus. ESA's Envision mission and NASA's Veritas mission, both currently planned for the 2030s, will dramatically improve our understanding of Venus's surface geology and volcanic activity, with far higher resolution radar mapping and other instruments. Let us now talk about the atmosphere of Venus in more detail, because it is intimately connected to the question of the retrograde rotation through the atmospheric tidal mechanism. The atmosphere of Venus at the surface level has a temperature of about 465 degrees Celsius and a pressure of about 92 atmospheres. As you ascend through the atmosphere, both temperature and pressure decrease. At about 50 kilometers altitude, the lower cloud layer, the temperature is around 75 degrees Celsius and the pressure is about 1 atmosphere, broadly similar to Earth's surface conditions. This is the altitude where the most Earth-like conditions in the Venus system exist. The clouds of Venus are organized in distinct layers between roughly 45 and 70 kilometers altitude. The lower clouds consist primarily of sulfuric acid droplets. The upper clouds are more diffuse. The clouds are highly reflective. The high albedo of about 0.75 is why Venus is so bright as seen from Earth. Above the cloud tops, the atmosphere continues to roughly 250 kilometers altitude before merging with the ionosphere and the boundary with the solar wind. The atmospheric circulation of Venus is remarkable. At cloud top altitudes of about 70 kilometers, the winds are extraordinarily fast, reaching about 360 kilometers per hour in the direction of the solar rotation. This super-rotation of the atmosphere is one of Venus's most puzzling features. The cloud tops complete a circuit around the planet in about 4 Earth days, 60 times faster than the surface rotation below them. The atmospheric superrotation means that an observer floating in the cloud tops would experience Venus rotating very differently from the surface. The 243-day surface sidereal rotation becomes irrelevant. The effective environmental period is the 4-day atmospheric circulation. The mechanism that maintains the atmospheric superrotation is not fully understood. Venus's atmospheric circulation is a major focus of ongoing research. Understanding it requires detailed modeling of how momentum is transported between different atmospheric layers. This atmospheric superrotation also has implications for the atmospheric tidal hypothesis for Venus's retrograde surface rotation. The same atmospheric dynamics that produce the superrotation also produce thermal tides, pressure waves driven by differential solar heating of the atmosphere. These thermal tides propagate through the atmosphere and exert a torque on the surface. The magnitude and direction of this torque depends on the atmospheric structure and circulation. The atmospheric thermal tide theory for Venus's retrograde rotation proposes that over billions of years, the torque from atmospheric thermal tides balanced the gravitational tidal torque from the Sun, leading to an equilibrium rotation state that is retrograde. Recent improvements in modeling this effect have made it more quantitatively viable than earlier estimates suggested. Let us now talk about one of the most recent and significant developments in understanding Venus's rotation, the discovery that Venus's rotation is not perfectly constant. Measurements from the ESA Venus Express mission, which orbited Venus from 2006 to 2015, compared the positions of surface features as seen in radar with the positions predicted from earlier Magellan observations. The comparison revealed that surface features had shifted by about 20 kilometers relative to their predicted positions. This displacement corresponds to Venus's rotation being slower during the Venus Express epoch than during the Magellan epoch, a difference of about 6.5 minutes per sidereal rotation. A change in the rotation period of 6.5 minutes over the approximately 16 years between the two missions. This is extraordinary. The rotation period of Venus, already anomalous in being retrograde and extremely slow, appears to vary on decade timescales. What could cause this variation? One possibility: exchange of angular momentum between Venus's atmosphere and its solid surface. On Earth, seasonal variations in the atmospheric circulation cause measurable changes in Earth's rotation period, measurable at the millisecond level over seasonal timescales. The effect is much smaller than what was measured for Venus, but the principle is the same. If Venus's atmospheric superrotation varies over time, perhaps responding to changes in solar heating, volcanic eruptions, or internal atmospheric dynamics, the atmosphere could exchange angular momentum with the surface, changing the surface rotation period. Given the enormous mass of Venus's atmosphere compared to Earth's, this effect could be much larger on Venus. The potential variation in Venus's rotation period opens new questions. If the atmosphere is exchanging angular momentum with the surface on this scale, what drives the atmospheric variations? Is there a long-period oscillation in Venus's atmospheric superrotation? Could volcanic events on Venus's surface measurably affect the rotation period through atmospheric loading? These questions are directly relevant to future missions. Envision and Veritas will both be able to track surface features with high precision and measure the rotation period more accurately than was possible with Magellan or Venus Express. Understanding whether Venus's rotation period varies and on what timescale and by how much is one of the key scientific objectives for the next generation of Venus missions. The rotation of Venus, anomalous, retrograde, and apparently variable, continues to reveal new aspects of planetary physics with each new measurement. Let us now talk about what all of this means for Venus as a potential habitat, because Venus was once considered a possible candidate for life, and its current state raises profound questions about what went wrong. In the 1950s and early 1960s, before any spacecraft had visited Venus, some scientists speculated that Venus might be a tropical world, warmer than Earth but possibly habitable, perhaps covered in swamps or oceans. The dense cloud cover was sometimes imagined to regulate temperature rather than causing the extreme greenhouse effect it actually produces. The Mariner 2 flyby in 1962 and subsequent missions rapidly disabused this notion. The surface temperature of 465 degrees Celsius makes Venus uninhabitable in any straightforward sense. No known biochemistry could function at this temperature. No liquid water could exist on the surface. But was Venus always like this? Climate models suggest that early Venus, perhaps 4 billion years ago, may have had liquid water on its surface. The Sun was about 25 to 30% less luminous in the early solar system, which would have reduced the heating Venus received. A Venus with lower luminosity input might have been in a regime where liquid surface water was stable. If Venus once had surface oceans, they are gone now. The process by which Venus lost its water, if it had any, and transitioned to its current state is connected to the concept of a runaway greenhouse effect. On Earth, the carbonate-silicate cycle regulates the amount of CO2 in the atmosphere. Atmospheric CO2 dissolves in rainwater, reacts with silicate rocks through chemical weathering, and is sequestered as carbonate minerals. Plate tectonic processes then recycle these carbonates back into the mantle, where the CO2 is released by volcanism and returned to the atmosphere. This creates a long-term thermostat that keeps Earth's temperature in a habitable range. On Venus, this regulatory cycle appears to have broken down, or perhaps never operated effectively. Whether this was due to Venus's greater proximity to the Sun, crossing a threshold for runaway warming, to the early loss of water that prevents weathering from operating, to the cessation of plate tectonics, or to some combination, is not fully resolved. The transition from a possibly habitable early Venus to the current hellscape happened at some point in the planet's history. Understanding when and why is one of the central scientific questions driving the renewed interest in Venus missions. Here, the retrograde rotation may play an indirect role. A slowly retrograde rotating planet has different atmospheric dynamics from a rapidly prograde rotating one. The nature and efficiency of the greenhouse effect depend on atmospheric circulation. The absence of a magnetic field, possibly connected to the slow rotation, affects how quickly the solar wind strips the upper atmosphere. These connections are suggestive, but not definitively established. Venus's evolution remains one of the most important unsolved problems in planetary science. Let us talk about what the recent phosphine controversy revealed about our understanding of Venus, and about how much we still do not know about the planet that rotates backwards in our sky. In September 2020, a team of astronomers led by Jane Greaves of Cardiff University announced the detection of phosphine, PH3, in the atmosphere of Venus at altitudes of approximately 50 to 60 kilometers. The detection was made using the James Clerk Maxwell Telescope in Hawaii and confirmed with the Atacama Large Millimeter Array in Chile. Phosphine is significant because on rocky planets it is not easily produced by known geological or atmospheric processes. On Earth, phosphine is produced almost exclusively by biological processes, by microorganisms in anaerobic environments. In the outer solar system, it is present in the atmospheres of Jupiter and Saturn, where high pressures can drive its formation through chemical reactions. But on a rocky planet like Venus, explaining a large abundance of phosphine without biological production is difficult. The announcement was significant enough that the scientific community took it seriously as a possible biosignature, a chemical signature that might indicate biological activity in the Venusian cloud layers. The subsequent investigation, however, has been contentious. Reanalysis of the original data found that the signal was much weaker than initially reported, possibly close to detection limits. The data processing method used in the original analysis was questioned. Further observations produced inconsistent results. As of now, the scientific community is not convinced that phosphine has been definitively detected in Venus's atmosphere. But the episode is instructive in several ways. First, the cloud layer of Venus at 50 to 60 kilometers altitude, where the temperature is roughly 0 to 60 degrees Celsius and the pressure is 0.4 to 2 atmospheres, is the most Earth-like environment in the inner solar system outside of Earth itself. If life could exist anywhere in the Venusian system, floating in this cloud layer is considered the most plausible location. Some organisms on Earth exist in acidic cloud droplets. The sulfuric acid content of Venus's cloud droplets is more extreme than any Earth environment, but life's capacity for adaptation to extreme chemistry is not fully known. Second, we have been studying Venus for 6 decades with spacecraft and ground-based observations, and the question of whether there are phosphine biosignatures in its atmosphere is still unresolved. This illustrates how difficult it is to characterize atmospheric composition from Earth or from orbital observations with current instruments. Third, the phosphine episode dramatically increased scientific interest in Venus and contributed to the prioritization of Venus missions in the Planetary Science Decadal Survey. The cloud habitability question, whether anything could live floating in the temperate cloud layer of a planet whose surface is a hellscape, is directly connected to Venus's atmospheric dynamics, which are in turn connected to its unusual rotation. The superrotating atmosphere, the specific cloud structure, the temperature and pressure profile, all are products of the global circulation, driven in part by the solar thermal forcing on a slowly retrograde rotating planet. Understanding why Venus rotates backwards is therefore not just a question about rotation. It is connected to understanding whether Venus's clouds could support life, whether Venus once had surface liquid water, why Venus evolved so differently from Earth despite similar bulk properties, and what this tells us about the conditions required for habitable planets around other stars. Let us now talk about the specific missions that are currently planned or under development that will dramatically improve our understanding of Venus and potentially answer the rotation question. 3 major Venus missions are currently approved or in development. Da Vinci, Deep Atmosphere Venus Investigation of Noble Gases, Chemistry and Imaging, is a NASA Discovery mission approved in 2021. It consists of a flyby spacecraft and an atmospheric entry probe. The probe will descend through Venus's atmosphere over about an hour, taking measurements of atmospheric composition, including noble gases and sulfur-bearing compounds, as it falls from the cloud tops toward the surface. It will also take images of Aphrodite Terra, a large highland region, from close range during its final kilometers of descent. Da Vinci will not orbit Venus. Its atmospheric measurements will provide constraints on Venus's origin and history by characterizing the noble gas content of the atmosphere. Isotopic ratios of argon, neon and krypton carry information about the origin of Venus's volatiles and the extent to which the atmosphere has been resupplied or modified over geological time. Envision is an ESA mission currently in development, expected to launch in the early 2030s. It will enter orbit around Venus and carry a synthetic aperture radar for surface mapping at resolution comparable to or better than Magellan, a sounder for probing the subsurface structure, a spectrometer suite for atmospheric and surface chemistry, and a radio science experiment. Envision is designed as a comprehensive characterization mission, attempting to understand Venus as a coupled system: interior, surface, atmosphere, magnetosphere. Critically for the rotation question, Envision will track surface features with high precision over its multi-year mission, allowing measurement of the rotation period and its possible variation at a level of precision better than any previous mission. If Venus's rotation period really does vary on decade timescales, as suggested by the Venus Express versus Magellan comparison, Envision will be able to characterize this variation in detail. Veritas, Venus Emissivity, Radio Science, INSAR, Topography and Spectroscopy, is a NASA discovery mission that was approved in 2021 but subsequently deprioritized due to budget constraints. It is currently delayed, with a launch date not set. Veritas would carry a radar system capable of mapping Venus's surface with higher resolution than Magellan, a near-infrared spectrometer for surface mineralogy mapping in windows where the dense atmosphere is partially transparent, and a precision radio tracking system for measuring Venus's gravity field and rotation. The combination of Da Vinci, Envision, and eventually Veritas would represent the most comprehensive investigation of Venus since the Magellan era, and would provide data to test competing models of Venus's origin, evolution, and current state, including the competing models for why it rotates backwards. A critical piece of data that none of these missions directly provides, at least not straightforwardly, is the current state of Venus's interior. We do not know whether Venus has a solid inner core like Earth, a liquid outer core, whether the core is currently cooling or has already solidified, or whether active convection exists in the mantle. All of these interior properties bear on the question of why Venus lacks a magnetic field, which in turn bears on the rotation dynamo connection. A seismometer on Venus's surface, capable of detecting Venus quakes and measuring the seismic velocity structure of the interior, would be the most direct way to characterize the interior. This is extraordinarily challenging because of the surface temperature. A conventional seismometer operating at 465 degrees Celsius would fail within minutes. Research into high-temperature electronics and mechanical systems that could survive on Venus's surface is ongoing, with some promising directions. A long-duration surface station on Venus capable of seismological measurements is a possible future mission concept, but not a near-term reality. Let us now talk about how the retrograde rotation of Venus fits into the broader context of other solar system bodies with unusual rotation states, because Venus is not entirely alone in being anomalous. Uranus rotates with an axial tilt of 97.77 degrees, essentially lying on its side, as we discussed in detail. Like Venus, this is well outside the range expected from the accretion process alone, and almost certainly results from one or more large collisions in Uranus's early history. Pluto rotates with an axial tilt of 122.5 degrees, also significantly tilted. Pluto and its large moon Charon are mutually tidally locked. Both always face the same hemispheres toward each other, and both have tilted axes. The system is thought to have been set up by a large impact that formed Charon. Mercury's rotation is in a 3:2 spin-orbit resonance with its orbital period. It rotates exactly 3 times for every 2 orbits around the Sun. This is the result of tidal evolution driven by solar tides. Mercury's current rotation state is a stable equilibrium maintained by the combination of the 3:2 resonance and Mercury's orbital eccentricity. Earth's moon is in a 1:1 spin-orbit resonance, tidally locked, rotating once per orbit so it always shows the same face to Earth. This is the tidal locking outcome. Titan, Saturn's large moon, is also in synchronous rotation, tidally locked to Saturn. Venus's retrograde rotation stands out even in this collection of anomalous rotation states. Most of the examples above result from tidally driven evolution towards stable resonant states. Mercury's 3:2 resonance, the Moon's 1:1 lock, Charon's mutual lock with Pluto. Uranus's extreme tilt is thought to be an impact origin, similar to one of the hypotheses for Venus. Venus's current rotation state is particularly unusual because it is not obviously in a simple tidal resonance. The 243-day retrograde rotation is not in an obvious simple ratio with Venus's 225-day orbital period. The near resonance between Venus's solar day, 116.75 days, and Earth's synodic period as seen from Venus, the time between closest approaches of Earth to Venus as seen from Venus, which is approximately 584 days, close to 5 times the 116.75-day solar day, has been noted. Some researchers have proposed that this near resonance could be dynamically meaningful, that Venus might be in a resonance with Earth's gravitational influence, though this remains speculative and controversial. Let us now talk about what the retrograde rotation means for a hypothetical observer standing on Venus's surface, for the experience of being on a planet whose sun rises in the west. If you stood on Venus's surface, setting aside the impossibility of survival at 465 degrees Celsius and 92 atmospheres, the first thing you would notice is that it is not dark. Not completely dark. The thick atmosphere scatters enough light even on the night side that the darkness is more like a very overcast night on Earth than the absolute darkness of space. The cloud layers glow faintly with scattered light even when the sun is below the horizon. When the sun does rise, it rises in the west. This follows directly from the retrograde rotation. Venus rotates from east to west rather than west to east, so the sun appears to move from west to east across the sky. The sun's motion across the sky is very slow. From sunrise to sunset, one Venusian half-day takes about 58 Earth days. The sun crawls across the sky. Its angular velocity is extremely slow, roughly 0.06 degrees per hour compared to Earth's half degree per hour. The sun's apparent size from Venus's surface is about 1.5 times its apparent size from Earth. Venus orbits closer to the sun. Through the clouds, which are omnipresent and opaque, the sun would appear as a bright disk or an undefined bright region in the cloud cover, rather than a sharp disk in a clear sky. The clouds are sulfuric acid. The temperature at the cloud base, 45 kilometers altitude, is about 75 degrees Celsius. The temperature increases as you descend toward the surface. The pressure at the base of the clouds is still only a few atmospheres. From the cloud base downward to the surface, there are 45 kilometers of clear but extremely hot and high-pressure CO2 atmosphere. At the surface, the atmosphere is so dense that it is more like a fluid than a gas in its optical properties. The refractive index of the atmosphere at surface pressure is significantly higher than at lower pressures, causing significant bending of light. Optical distortions would make distant objects appear to curve upward. The horizon would appear to be raised, as if you are standing at the bottom of a bowl. The sky from Venus's surface, looking upward through the dense CO2, would appear orange or yellow-orange, with the scattered light from the sun diffused through the thick atmosphere. No stars would be visible. No moon. Venus has no moon. No other planets would be visible through the opaque clouds. The sun would be a bright, glowing region in the clouds, identifiable but not a sharp disk. During the day, the 58-day-long Venusian day, this bright region would slowly move from west to east across the sky overhead. Everything about this experience reflects the retrograde rotation, the direction of sunrise, the direction of the sun's motion, the length of the day. The sun rising and setting at a pace that makes Earth's seasons look frantic. Let us now talk about the question that is perhaps most relevant for the long-term future, about what Venus's retrograde rotation tells us about the diversity of planetary outcomes around other stars. The discovery of exoplanets, planets around other stars, has revealed that planetary systems are extraordinarily diverse. Planets in orbits and sizes that do not exist in our solar system are common around other stars. Gas giants as close to their stars as Mercury is to the Sun. Super-Earths, planets larger than Earth but smaller than Neptune, which have no analogue in our solar system. Multi-planet systems packed much more tightly than the inner planets of our solar system. Within this diversity, Venus poses a specific question. How common are planets that, despite forming in a star's habitable zone, and despite being roughly Earth-sized, end up in a radically different state? If Venus's retrograde rotation is connected to a catastrophic early impact, then it is a product of the inherently stochastic nature of planetary accretion. Large late impacts are random. Any rocky planet in any system has some probability of experiencing such an impact. The probability depends on the specific conditions of the system, the number and mass distribution of remaining planetesimals, the architecture of the outer system, the presence of giant planets that can scatter small bodies. If Venus's retrograde rotation and current hellish state are primarily the product of atmospheric tidal evolution from a more normal initial state, then they raise the question of whether any rocky planet in the inner habitable zone of a Sun-like star might evolve towards similar conditions over billions of years. Either way, Venus suggests that having an Earth-sized planet in the habitable zone of a Sun-like star does not guarantee an Earth-like outcome. The range of possible outcomes for such a planet is large. Venus demonstrates the extreme. For the search for habitable planets around other stars, this matters. When we detect an Earth-sized planet in the habitable zone of a Sun-like star and try to assess its habitability, the question of its rotation state is relevant. A slowly rotating planet, or a retrograde rotating planet, may have atmospheric dynamics that drive it toward a greenhouse runaway rather than a stable, temperate climate. Measuring the rotation rates of Earth-sized exoplanets is currently beyond our capabilities, but future observational developments may eventually make it possible. The James Webb Space Telescope can observe the thermal emission from the day side and night side of very close-in rocky exoplanets and infer whether the atmosphere redistributes heat efficiently. This is related to, but not equivalent to, measuring rotation rate directly. Future missions designed for atmospheric spectroscopy of habitable zone rocky planets, including possible designs like the Habitable Worlds Observatory, might eventually observe indirect signatures of rotation. Venus in our solar system is the control case. It is the one example we have of what happens when an Earth-sized planet does not develop the way Earth did. Understanding its rotation, understanding why it flipped, or why it slowed and reversed, or why it was always different, is part of understanding how common or rare Earth-like planets actually are in the galaxy. Let us now talk about one more aspect of Venus that is directly relevant to the rotation question: the question of whether Venus is currently geologically active, and how that activity connects to the rotation through atmospheric coupling. The evidence for current or recent geological activity on Venus has been accumulating. The 2023 detection of a changing volcanic vent in Magellan data was the most direct evidence yet. Earlier, Venus Express detected localized hotspots in the infrared emission from certain regions of the surface, possible thermal signatures of recent lava flows. The distribution of sulfur dioxide in the atmosphere appears to vary on decade timescales, consistent with episodic injection from volcanic eruptions. If Venus is geologically active, and the evidence increasingly suggests it is, this activity has implications for the atmospheric composition, which has implications for the atmospheric thermal tides, which has implications for the equilibrium rotation state. Volcanic eruptions on Venus inject sulfur dioxide into the atmosphere. Sulfur dioxide reacts with water vapor and is converted to sulfuric acid, the dominant cloud material. Changes in the sulfuric acid content of the clouds would change their albedo, which changes the amount of sunlight absorbed by the atmosphere, which changes the thermal tide pattern, which could potentially affect the torque on the solid surface. This is a complex chain of causation, but it suggests that Venus's rotation is not simply a static remnant of ancient history. It may be a dynamically maintained equilibrium that is sensitive to ongoing geological activity. If Venus undergoes episodic large volcanic events, if the catastrophic resurfacing model is correct, and Venus periodically undergoes massive volcanic activity, followed by quiescent periods, then the atmospheric composition and cloud structure might change dramatically on geological timescales. These changes would alter the atmospheric thermal tides, and therefore alter the torque balance that determines the equilibrium rotation rate. The possible variation in Venus's rotation period observed between the Magellan and Venus Express eras, the 6.5-minute change, could be an early hint of this kind of coupling between geological activity, atmospheric response, and rotation. Understanding whether this coupling exists and at what level requires the kind of long-term monitoring that Envision will provide. By precisely tracking surface features over its multi-year orbital mission, Envision will determine whether the rotation period is constant or varying, and by how much. Combined with its monitoring of atmospheric composition and surface thermal emission, it may be possible to correlate rotation rate changes with atmospheric and geological events. This would be extraordinary, directly observing the coupling between a planet's geology, its atmosphere, and its rotation on human timescales. Venus is the only planet in our solar system where this coupling might be strong enough and the rotation period short enough to observe such changes within a single mission lifetime. The retrograde rotating, slowly spinning, atmospherically active, geologically restless planet in our inner solar system, wrong in so many ways compared to our expectations, may turn out to be the most informative object in the solar system for understanding how rocky planets work as integrated systems. Let us now talk about what has been learned about Venus from the perspectives of atmospheric chemistry, specifically about the sulfur cycle, which is intimately connected to the cloud system and to the atmospheric dynamics driven by the unusual rotation. The sulfur cycle of Venus operates through several steps. Sulfur dioxide is emitted from volcanic activity at the surface and lower atmosphere. It rises through the atmosphere and at cloud altitudes combines with water vapor and oxygen to form sulfuric acid, H2SO4. The sulfuric acid condenses to form droplets that make up the cloud layers. Within the clouds, the droplets can evaporate and sulfuric acid vapor can decompose back to sulfur dioxide and water under the influence of ultraviolet radiation from the sun. Sulfur compounds cycle through the clouds in a complex chemical loop. This sulfur cycle has a known problem. The upper clouds contain more sulfuric acid than simple photochemical models predict, and there appears to be an unknown UV absorber in the upper cloud layers. Something is absorbing ultraviolet light in a way that pure sulfuric acid does not. The nature of this UV absorber is unknown. Proposed candidates include ferric chloride, elemental sulfur allotropes, and biological molecules. The biological explanation is speculative. The chemical explanations are also not fully satisfying. The atmospheric superrotation, that 4-day circulation of the cloud tops, is what makes this sulfur cycle operable across the entire planet. Without the rapid circulation, the chemical products of solar UV photolysis would not be redistributed. The cloud system would become inhomogeneous and concentrated on the day side. The current globally uniform cloud deck is a product of both the chemistry and the circulation. And the circulation itself, how it is driven and maintained, is connected to the thermal structure of the atmosphere, which is connected to how solar heating is distributed, which is connected to the rotation rate. A different rotation rate would produce a different thermal tide pattern, a different atmospheric circulation, a different cloud distribution. Venus is a coupled system. The rotation determines the atmospheric dynamics. The atmospheric dynamics determine the chemical cycles. The chemical cycles determine the cloud structure. The cloud structure determines the albedo. The albedo determines how much solar heating the atmosphere receives. The heating drives the thermal tides. The thermal tides exert a torque on the solid planet. The torque influences the rotation, a complete circle. The rotation influences itself through the atmosphere. This coupling is what makes the atmospheric tidal hypothesis for Venus's retrograde rotation compelling, and also what makes it so difficult to pin down precisely. The system has multiple feedbacks, and the equilibrium rotation rate depends on the balance of all of them simultaneously. Understanding this coupled system, rotation, atmosphere, chemistry, clouds, is the central scientific challenge of Venus research. And it is the reason that every new mission to Venus is designed with multiple instruments spanning multiple disciplines, rather than focusing on any single measurement. Venus does not yield its secrets to simple questions. It requires understanding the whole system at once. Let us talk about what Venus's retrograde rotation means in the context of one of the most active areas of current planetary science, the study of the early solar system and the role of giant planet migration in shaping the inner planets. The Grand Tack hypothesis, developed by Kevin Walsh and colleagues and published in 2011, proposes that Jupiter formed beyond the snow line in the outer solar system and then migrated inward, reaching as close as 1.5 astronomical units from the Sun, before being captured in a resonance with Saturn and migrating back outward to its current position. This inward then outward migration, the tack, like a sailing ship changing direction, would have scattered the inner solar system profoundly. The passage of Jupiter through the inner solar system would have swept away much of the primordial inner solar system material. The 4 rocky planets that eventually formed, Mercury, Venus, Earth, Mars, formed from a dynamically depleted disk of material. This explains several features of the inner solar system: the relatively small mass of Mars compared to Earth, Mars formed in a depleted zone, the asteroid belt structure, and the specific compositional gradients of the inner planets. In the context of the Grand Tack, the late stages of inner planet formation would have involved accretion from a relatively sparse and dynamically excited disk. The final few large impactors that each planet accumulated, those that determined the final rotation states, would have come from a dynamically stirred population with higher impact velocities and more varied impact geometries than in a quiescent disk. This might make unusual outcomes, like Venus's retrograde rotation, more likely than they would be in simpler models of inner solar system formation. More recently, the Nice model and its successors proposed that the giant planets underwent a period of instability, possibly triggered by gravitational interactions among themselves, several 100 million years after the solar system formed. This instability drove a period of intense bombardment of the inner solar system, the Late Heavy Bombardment, recorded in the impact record on the Moon. During this bombardment, the inner planets received large impactors from the scattered outer solar system population. A large impactor during the Late Heavy Bombardment, arriving at Venus at the right angle and speed, could have delivered the angular momentum needed to flip Venus's rotation axis, or could have accelerated a pre-existing slow retrograde rotation. If this scenario is correct, the timing of Venus's rotation becoming anomalous would be around 3.8 to 4.1 billion years ago, the approximate epoch of the Late Heavy Bombardment. This is deep in Venus's past and leaves no directly observable record today. But there is an indirect test. If a large impact created Venus's retrograde rotation during the Late Heavy Bombardment, the impact would have melted a large fraction of Venus's surface, reset the surface geology, and possibly contributed to the loss of early water. The timing and scale of the resurfacing event in Venus's geological record which global models suggest happened around 300 to 600 million years ago, does not obviously match the late heavy bombardment timing of 3.8 to 4.1 billion years ago. This discrepancy suggests that either the resurfacing event and the rotation changing event are separate episodes, or the impact hypothesis for the retrograde rotation is incorrect. These questions are at the frontier of planetary science and require better data about Venus's interior structure, the timing of geological events in its history, and the isotopic composition of its atmosphere, exactly the data that Da Vinci, Envision, and Veritas are designed to provide. Let us now talk about a specific observational feature of Venus that is related to the rotation: the peculiar relationship between Venus and Earth in terms of inferior conjunctions. Venus orbits the Sun inside Earth's orbit. Periodically, Venus passes between the Sun and Earth. This is called inferior conjunction. At inferior conjunction, Venus is at its closest to Earth, as close as 38 million kilometers. The remarkable fact is that whenever Venus is at inferior conjunction and closest to Earth, it consistently presents almost exactly the same face toward Earth. The same side of Venus faces us at every close approach. This is not a coincidence. It is a consequence of the near resonance between Venus's rotation period, 243.025 days, and the synodic period of Venus as seen from Earth, the time between successive inferior conjunctions, which is approximately 583.9 days. 583.9 days divided by 243.025 days is very close to 2.4, and more precisely, 583.9 approximately equals 2.405 times 243.025. This means that Venus completes almost exactly 2.4 rotations between successive inferior conjunctions. Over 5 synodic periods, 5 times 583.9 equals 2,919.5 days, Venus completes 2,919.5 over 243.025, approximately equals 12.016 rotations. Almost exactly 12 rotations in 5 synodic periods. In other words, after 5 inferior conjunctions, Venus has rotated almost exactly the same angle relative to the stars, and therefore presents almost the same face toward Earth at each conjunction. This near resonance raises a question. Is it coincidental, or is it maintained by a real gravitational interaction between Earth and Venus? If it is a genuine resonance, if Earth's gravitational pull on Venus slightly adjusts Venus's rotation to maintain this relationship, then it would be a remarkable example of one planet's rotation being tidally influenced not by its parent star, but by a neighboring planet. Some researchers have proposed exactly this. The argument is that Earth's gravitational torque on Venus, while very small, much smaller than the Sun's, might be sufficient to maintain this resonance in a way that keeps Venus's rotation frequency slightly adjusted. This would require the resonance to be stable and Venus's rotation to be sensitive to such small perturbations. The question remains contested. Most analyses suggest that Earth's tidal influence on Venus is too small to maintain a strict resonance, and the near-integer relationship may be a coincidence. But the near resonance is precise enough that it cannot be dismissed without careful analysis. If it is a genuine Earth-Venus resonance, it would add another layer to the story of Venus's rotation, not just an anomaly from the distant past, but an ongoing gravitational interaction with its nearest planetary neighbour. Let us now talk about the temperature contrast between the day and night sides of Venus and what it reveals about the atmospheric dynamics driven by the slow retrograde rotation. On Earth, the day-night temperature contrast at the surface is significant, from warm days to cool nights, a variation of typically tens of degrees in temperate regions. This contrast drives atmospheric circulation, creates weather patterns, and establishes the diurnal cycle that almost all life on Earth depends on. On Venus, despite a day lasting 58 Earth days, the surface temperature contrast between day and night sides is remarkably small, less than a few degrees Celsius. The surface temperature everywhere on Venus is close to 465 degrees Celsius, regardless of whether it is in the middle of the day or the middle of the night. This thermal homogeneity is a consequence of the dense atmosphere. The atmosphere holds so much heat, the thermal mass of 92 atmospheres of CO2 is enormous, that 58 days of night is insufficient to measurably cool it. The atmosphere acts as a global thermal buffer, distributing heat from the day side to the night side efficiently enough to maintain near uniform surface temperatures. This behavior is in stark contrast to other slowly rotating bodies. The Moon, which also has a slow rotation relative to the Sun, a lunar day is about 29.5 Earth days, has an extreme day-night temperature contrast of about 300 degrees Celsius, because it has essentially no atmosphere to redistribute heat. Mercury, with a sidereal rotation of 58.6 days and essentially no atmosphere, also has extreme temperature contrasts, surface temperatures ranging from over 400 degrees Celsius on the day side to minus 170 degrees on the night side. Venus, same slow rotation but with a massive atmosphere, shows no such contrast. The atmosphere is everything. This comparison illustrates a crucial point about planetary science. The rotation rate of a planet affects its atmospheric dynamics, which in turn determines the temperature distribution, which determines many other aspects of the planet's climate and potential habitability. But the rotation rate does not determine these things in isolation. It interacts with the atmosphere, the surface composition, the geology, the solar heating, and all the other components of the coupled planetary system. Venus is the most dramatic example of this coupling. Its slow retrograde rotation would, in isolation, suggest extreme day-night temperature contrasts. But the massive atmosphere negates this expectation entirely. Let us now talk about what missions to Venus have physically experienced on the surface. About the Soviet Venera program, the only missions that have ever successfully operated on Venus's surface, and what they revealed. Between 1970 and 1985, the Soviet space program landed 10 spacecraft on Venus's surface and obtained data from each of them before they were destroyed by the environment. The Venera landers are the only spacecraft ever to operate on the surface of Venus. The first successful soft landing, Venera 7 in December 1970, transmitted data for 23 minutes before being destroyed. This was the first soft landing on any planet other than the Moon, and the first transmission of data from the surface of another planet. Subsequent Venera missions landed, survived longer, up to about 110 minutes, and returned increasingly detailed data. Venera 9 and Venera 10 in 1975 returned the first photographs from the surface of another planet. The images showed a landscape of angular rocks with sharp edges scattered across a fractured surface, not rounded and weathered as might be expected if the planet had ever had flowing water. The rocks were sitting on a flat bedrock surface. The lighting was dim, about equivalent to an overcast day on Earth. Venera 11 and 12 in 1978 detected lightning, electrical discharges in Venus's atmosphere. Venera 13 and 14 in 1982 returned the first colour photographs from Venus's surface, showing orange-brown rocks and fine-grained material. They also drilled into the surface and analysed the composition, finding basaltic rock similar to oceanic basalts on Earth. The Venera 15 and 16 missions in 1983 were orbiters that carried synthetic aperture radars and mapped the northern quarter of Venus's surface at resolutions of a few kilometers, the first significant radar mapping of Venus. What strikes about the Venera lander images is the sharpness and angularity of the rocks. Erosion on Venus appears to be primarily wind-driven rather than water-driven. And the wind erosion at Venus's surface is limited because the dense CO2 atmosphere moves very slowly despite the super-rotating cloud tops far above. The surface winds are only a few kilometers per hour. The dense atmosphere transmits force even at low wind speeds. But erosion rates are geologically slow. The rocks we see in Venera images are sitting essentially as they were emplaced, by volcanic activity or by impact, and have been modified only slowly by the hot, dense atmospheric chemistry. These Venera surface images represent 40-year-old data. The most recent image from Venus's surface is from 1982. We have not returned since. This 40-year gap in surface data is a consequence of the extreme difficulty of operating on Venus's surface. The temperature and pressure that destroy conventional electronics within hours are the same conditions that make long-duration surface operations extraordinarily difficult with current technology. Research into high-temperature electronics has advanced significantly since the Venera era. Silicon carbide and gallium nitride semiconductors can operate at temperatures up to several hundred degrees Celsius. New approaches to mechanical sensing using entirely different materials from silicon, such as silicon carbide MEMS sensors, show promise. The Glenn Research Center at NASA has developed and tested prototype high-temperature electronics specifically aimed at Venus surface operations. A future surface mission with electronics capable of surviving for days or weeks rather than hours would transform our understanding of Venus's geology, interior, and the question of active volcanism. But no such mission is currently approved. The technology is not yet ready for deployment. The Venera images, those orange-brown angular rocks in the dim orange light, remain the only direct visual record of Venus's surface environment. They show a planet that is utterly hostile, yet geologically recognizable. Basaltic rocks, volcanic plains, a place that is physically understandable, even if environmentally impossible for humans. Let us now talk about what Venus can tell us about the concept of planetary habitability more broadly, about the parameters that determine whether a rocky planet can maintain conditions suitable for life over geological timescales. The habitable zone around a star, the range of orbital distances where liquid surface water can exist, is calculated based on several factors including stellar luminosity, planetary albedo, and the greenhouse effect of the atmosphere. Venus sits at the inner edge of the Sun's habitable zone, or slightly interior to it, making it an important test case for the inner boundary of habitability. The inner edge of the habitable zone is determined by the onset of runaway greenhouse conditions. As a planet receives more stellar flux, either because it is closer to its star or because its star brightens over time, the surface temperature increases, more water evaporates, water vapor amplifies the greenhouse effect, more water evaporates, and eventually all surface liquid water is lost to a moist greenhouse runaway. The water then photodissociates in the upper atmosphere and the hydrogen is lost to space. Venus may have crossed this threshold at some point in its history. The Sun has brightened by about 25 to 30% since the solar system formed. Early Venus, with a dimmer Sun, might have been below the runaway greenhouse threshold. As the Sun brightened over billions of years, Venus may have crossed the threshold and been driven to its current hellish state. If this is the correct story, it implies that Earth will also cross the inner habitable zone threshold in the future, perhaps in about 1 to 2 billion years, as the Sun continues to brighten. Earth's fate may eventually be a Venus-like state, but the rotation complicates this. Recent climate modelling work, particularly by studies from groups including those using the ROC 3D and ExoCam climate models, suggests that the rotation rate of a planet significantly affects where the inner edge of the habitable zone falls. Slowly rotating planets tend to have stronger day-night temperature contrasts, at least without a massive atmosphere, which affects cloud distribution, which affects albedo, which affects the heat balance. More importantly, planets that rotate slowly and synchronously, tidally locked to their star, may actually be more resistant to runaway greenhouse because of the formation of persistent cloud decks on the day side that reflect sunlight. The inner edge of the habitable zone for slowly rotating or tidally locked planets may be closer to the star than for rapidly rotating planets like Earth. Venus's particular situation, slow retrograde rotation, does not map cleanly onto either the synchronous or the rapidly rotating limit. It falls in an intermediate regime that is more difficult to model. The current view is that Venus's slow rotation creates an atmospheric circulation that is intermediate between the tidally locked pattern and the rapidly rotating pattern, and that this intermediate circulation may actually be less favourable for maintaining a stable, temperate climate than either of the extreme cases. This is an active area of research. The question of whether Venus's rotation rate contributed to the loss of its habitable conditions, or whether the runaway greenhouse was inevitable regardless of rotation rate, bears directly on estimates of how many planets in other systems are actually habitable. Every improvement in our understanding of Venus's climate, its rotation, and the coupling between them refines our models of habitable zone boundaries, and therefore refines our estimates of how many potentially habitable planets exist in the galaxy. Let us now talk about one more thing, about what Venus's anomalous rotation tells us in the most general terms about scientific understanding and about the value of outliers. Venus is an outlier. It does the wrong thing. It rotates in the wrong direction. It has no magnetic field despite being roughly Earth-sized. It has no large moon. It is covered in sulfuric acid clouds. It has a surface hot enough to melt lead. It shows no Earth-like plate tectonics. Each of these anomalies is a puzzle, and each puzzle is an opportunity. Anomalies are where our understanding is incomplete. Explaining why Venus is wrong in all these specific ways, requires developing physics and chemistry that explains not just the normal cases, but the exceptional ones. The atmospheric tidal theory, developed to explain Venus's rotation, has implications for understanding atmospheric dynamics on all slowly rotating planets. The study of Venus's runaway greenhouse has given us better models of climate stability on Earth and on exoplanets. The study of Venus's interior, its possible lack of a dynamo, its different tectonic regime, pushes our understanding of planetary interiors beyond the comfortable familiarity of Earth's interior. Science advances fastest at the edges of its current understanding. Venus is all edges. Every measurement of Venus reveals something that does not fit simple extrapolation from Earth. Every mission to Venus returns data that requires new explanations. This is why the planetary science community, after decades of relatively sparse Venus missions compared to Mars, has renewed its interest in Venus with 3 new missions approved or in development. Not because Venus is the most likely place to find life, it is not. Not because Venus is the easiest destination, it is one of the most difficult. But because Venus is the most instructive anomaly in our immediate cosmic neighborhood. The planet that should be Earth's twin and is instead its opposite. The planet whose sun rises in the west and sets in the east. The planet that has been orbited and overflown and descended into and landed on, and whose fundamental questions remain unresolved 40 years after the last surface mission. Why does Venus spin in the opposite direction? We do not know for certain. We have hypotheses, we have constraints, we have models that fit the current state. We have upcoming missions that will refine our understanding. But the answer, whatever it is, will tell us something important about how rocky planets work. About how the random events of planetary formation shape worlds across billions of years. About how rotation and atmosphere and geology and climate couple into systems that can evolve in radically different directions from seemingly similar starting conditions. Venus is asking a question we do not yet fully understand. The search for the answer is what planetary science is for. Let us talk about something that gives the question of Venus's rotation a very specific and immediate observational context. About Venus as it appears in the sky right now, and what that appearance means. Venus is the brightest object in the night sky after the Moon. Its apparent magnitude at maximum brightness reaches about -4.9, roughly 25 times brighter than Sirius, the brightest star. At certain apparitions, Venus is bright enough to cast a faint shadow on a dark night. It is easily visible in daylight if you know where to look. This extraordinary brightness is a direct consequence of the same thick sulfuric acid cloud cover that makes the surface so extreme. The clouds reflect about 75% of incoming sunlight, a geometric albedo of about 0.65. Venus is so bright precisely because its clouds are so opaque. Those clouds, the source of its brightness, are the same clouds whose atmospheric dynamics may be responsible for its retrograde rotation through the atmospheric tidal mechanism. The retrograde rotation you are trying to understand when you look at Venus is causally connected to the very brightness that makes it so conspicuous. Venus appears in the sky either as a morning star, rising before the sun in the east, or as an evening star, setting after the sun in the west. It never appears in the middle of the night when the sky is fully dark, because it orbits inside Earth's orbit, and therefore is always seen in roughly the same direction as the sun. The maximum angular separation between Venus and the sun, called greatest elongation, is about 47 degrees. This means Venus never rises more than about 3 hours before sunrise, or sets more than about 3 hours after sunset. The phases of Venus mirror those of the Moon in their origin. When Venus is on the far side of the Sun from Earth, near superior conjunction, it appears fully illuminated but small in angular size. When Venus is between Earth and the Sun, near inferior conjunction, its illuminated crescent is thin, but its angular size is large because it is close to Earth. At maximum elongation, Venus is roughly half illuminated, like a quarter moon. Galileo observed the phases of Venus in 1610 and recognized that they could only be explained if Venus orbited the Sun rather than the Earth, a direct observational proof of the heliocentric model. Venus's phases were among the early pieces of evidence that overturned the geocentric universe. This historical significance is worth pausing on. The planet whose rotation we are trying to understand tonight was central to one of the most consequential revolutions in human intellectual history. Galileo's Venus showed that Ptolemy was wrong. The planet that rises in the west, whose sun sets in the east, was a key instrument in establishing that Earth moves around the Sun rather than the other way round. The retrograde rotation of Venus adds a layer of irony to this history. The planet that proved Earth orbits the Sun is itself the one that spins in the opposite direction to its own orbit. Let us now talk about the contrast between what we know about the two most similar planets, Earth and Venus, and what the differences tell us about the contingency of planetary evolution. Earth and Venus formed from the same disk of material around the same star at roughly the same time. Their bulk properties are similar to a degree that no other pair of planets in the solar system matches. And yet, Earth has a rotation period of 24 hours. Venus has 243 days. Earth rotates prograde. Venus rotates retrograde. Earth has a large moon. Venus has none. Earth has a strong magnetic field. Venus has essentially none. Earth has liquid water oceans covering 71% of its surface. Venus has no liquid water. Earth has plate tectonics actively recycling its surface. Venus's tectonic style is different and possibly episodic. Earth has surface temperatures averaging 15 degrees Celsius. Venus has 465 degrees Celsius. Earth has an atmosphere of 1 bar, mostly nitrogen and oxygen. Venus has 92 bars of CO2. Earth has over 8 million known species of life. Venus has 0 confirmed biology. The differences are total. In every dimension relevant to habitability, the planets are opposites despite similar bulk properties. This is the central mystery of Venus, not just the rotation, but the entire suite of differences from Earth. The rotation is connected to many of the other differences. The lack of a moon may be connected to the impact history that affected the rotation. The lack of a magnetic field may be connected to the slow rotation. The atmospheric dynamics responsible for the runaway greenhouse are connected to the rotation through the tidal coupling. The rotation may not be the root cause of all the differences, but it is deeply entangled with them. This entanglement suggests that understanding the rotation requires understanding the whole Venus system. And understanding the whole Venus system requires understanding the chain of events, the specific sequence of impacts, migrations, tidal evolutions, atmospheric transitions that diverged from Earth's history at some specific point and led to such radically different outcomes. The divergence point is unknown. Was it always different? A different impact history during formation? Did it diverge early? Loss of water in the first billion years? Did it diverge gradually? Slow tidal evolution over 4 billion years? Different hypotheses imply different divergence points. The impact hypothesis implies a relatively early and sudden divergence. The tidal hypothesis implies a gradual divergence over geological time. The combination hypothesis implies multiple events at different times. Determining which scenario is correct is one of the major scientific objectives of the next generation of Venus missions. Let us now talk about what the question of Venus's retrograde rotation looks like from the perspective of comparative planetology, the study of planets as a class of objects rather than as individual cases. The solar system contains 4 rocky planets: Mercury, Venus, Earth, and Mars. Among these 4, Mercury, tidally influenced rotation in 3:2 spin-orbit resonance with its orbital period. Essentially no atmosphere, no magnetic field in the standard sense, actually a weak one from the core. Surface temperature extremes. Venus, retrograde rotation with extremely long period, massive CO2 atmosphere, no intrinsic magnetic field, no moon, runaway greenhouse, no plate tectonics in Earth style. Earth, prograde rotation with 24-hour period, moderate nitrogen-oxygen atmosphere, strong magnetic field generated by liquid iron outer core, large moon, liquid water oceans, plate tectonics, life. Mars, prograde rotation with 24-hour 37-minute period, thin CO2 atmosphere, about 0.6% of Earth's surface pressure, no current global magnetic field, evidence of past field, no moons of significance. Phobos and Deimos are tiny captured asteroids. No liquid surface water currently, inactive volcanically. The range of outcomes across 4 rocky planets formed from the same disk around the same star is extraordinary. No 2 are alike. Each has taken a different evolutionary path. The rotation rates span from Mercury's 58.6 Earth days through Venus's 243 days to Earth's 24 hours to Mars's 24.6 hours. The axial tilts span from Mercury's 0.03 degrees through Venus's effective 177 degrees to Earth's 23.4 degrees to Mars's 25.2 degrees. This diversity argues against any simple deterministic story of rocky planet evolution. The same initial conditions, similar bulk composition, similar orbital locations, can produce wildly different outcomes. Stochasticity matters. The specific sequence of large impacts in the late stages of accretion, the specific timing and magnitude of tidal evolution, the specific atmospheric history, all of these random dependent processes contribute to the final state. Venus is not special in being different from Earth. All 4 rocky planets are different from each other. Venus is simply the most different in the ways that matter most for habitability. This diversity in our own solar system, 4 planets, 4 wildly different outcomes, implies enormous diversity among the rocky planets of other stars. Among the thousands of rocky exoplanets we know about, and the hundreds of billions that likely exist in the galaxy, the range of rotation states, atmospheric compositions, magnetic field strengths, and surface conditions is almost certainly vast. Some fraction of those planets, perhaps a small fraction, perhaps a large fraction, we do not know, will have converged on conditions similar to Earth's. Understanding what produced Earth's particular outcome, including its particular rotation state, requires understanding why the other outcomes occurred. Venus is our best laboratory for this investigation. Let us now talk about one specific research question that connects Venus's retrograde rotation to the most cutting-edge observational capabilities now coming online: the potential measurement of atmospheric dynamics from the ground and from space. Venus's atmospheric superrotation, the 4-day circulation of the cloud tops, can be tracked by observing cloud features from Earth. The movement of cloud patterns visible in the ultraviolet light being absorbed differently by different chemical constituents in the clouds, reveals wind speeds at cloud top altitudes. Japan's Akatsuki mission, the only currently operational spacecraft at Venus, has been in orbit since December 2015. It carries cameras sensitive to ultraviolet, visible, near-infrared and thermal infrared wavelengths. Its primary mission is to study the atmospheric dynamics of Venus, the superrotation, the thermal structure, the cloud morphology. Akatsuki has revealed remarkable features in Venus's atmospheric dynamics. Stationary wave features, bright arcs or streaks that remain fixed relative to the surface despite the superrotating atmosphere flowing over them. These stationary waves appear above topographic features on the surface and propagate upward through the atmosphere. They are evidence that the solid surface, and therefore the rotation of the solid body, influences the atmospheric circulation even at high altitudes. The gravity waves generated by topography on the slowly rotating surface propagate upward and interact with the faster-moving cloud layers. This is a direct physical link between the surface rotation and the atmospheric dynamics, the kind of coupling that is central to understanding whether atmospheric tides can maintain the retrograde rotation equilibrium. Akatsuki's observations have also revealed unexpected large-scale wave phenomena in Venus's atmosphere, including a bow-shaped wave feature that stretched across the entire planet for several days in 2015 to 2016. The origin of this planetary-scale wave is debated, but appears related to topography on the surface below. These observations are directly relevant to the atmospheric tidal mechanism. If surface topography influences the cloud level dynamics, and if those dynamics determine the atmospheric torque on the surface, then the specific topography of Venus matters for the rotation equilibrium. This creates a feedback. The rotation rate determines the surface topography indirectly through volcanic and tectonic history. The topography drives atmospheric waves. The atmospheric waves contribute to the atmospheric tide. The atmospheric tide influences the rotation rate. This is a complex, non-linear feedback that is extremely difficult to model from first principles, but Akatsuki's observations are beginning to reveal the details of how it operates in practice. The combination of Akatsuki's ongoing observations, the forthcoming Envision mission's long-term atmospheric monitoring, and increasingly sophisticated atmospheric models is likely to substantially advance our understanding of this coupling within the next decade. Let us now talk about the long history of Venus exploration and about what that history reveals about the challenges of studying this planet. The exploration of Venus began early in the space age. The Soviet Union and the United States raced to be the first to reach Venus. The first spacecraft to successfully fly past Venus was Mariner 2 in December 1962, confirming the high surface temperatures and providing the first in situ measurements of the solar wind. The Soviet Venera program attempted more than a dozen missions to Venus between 1961 and 1985, with varying success. The early missions failed in various ways. Venera 1 lost contact before reaching Venus. Venera 3 reached Venus, but its communication system failed before transmitting surface data. Venera 4 returned the first data from Venus's atmosphere in 1967, but was crushed by the pressure before reaching the surface. Venera 5 and 6 was similarly crushed at altitude. Venera 7 reached the surface and survived long enough to transmit data, the first success. The iterative Soviet approach, learning from each failure, redesigning the next mission, is one of the remarkable engineering stories of the space age. The Venera spacecraft that successfully landed were built like pressure vessels, essentially submarines adapted for the Venusian pressure and temperature. They were designed to survive for about an hour, just long enough to complete their scientific measurements before the environment destroyed them. The American exploration of Venus has been more intermittent. Mariner 2 and Mariner 5 were flyby missions. Pioneer Venus 1 and 2 in 1978 were an orbiter and a multi-probe mission that deployed 4 atmospheric probes simultaneously. The Magellan mission from 1990 to 1994 was the most successful American Venus mission. It mapped essentially the entire surface with synthetic aperture radar and provided the best global view of Venus's geology. After Magellan ended in 1994, deliberately plunged into Venus's atmosphere to provide atmospheric data during its final descent, no American spacecraft returned to Venus until the Galileo spacecraft's flyby in 1990 and Cassini's flybys in 1999, both on their way to other destinations. The Messenger spacecraft flew past Venus twice in 2006 and 2007 on its way to Mercury. There is currently a 30-year gap between the end of the Magellan mission in 1994 and the next dedicated American mission. Da Vinci is planned for launch in the late 2020s. This gap is longer than the gap between Apollo 17 in 1972 and the next major moon program. During this 30-year gap, the question of Venus's retrograde rotation has not been resolved. The question of Venus's current geological activity has not been resolved. The question of whether early Venus had liquid water has not been resolved. The question of whether Venus's clouds could support life, raised dramatically by the phosphine controversy in 2020, has not been resolved. These open questions are not resolvable from Earth with remote observations. They require spacecraft. And the 30-year gap means we have simply not had the data to make progress. This is the context for the renewed interest in Venus. The Planetary Science Decadal Survey recognized that our knowledge of Venus has not kept pace with our knowledge of other planets, and that the questions Venus poses are fundamental enough to justify significant new investment. Da Vinci and Envision are the result of that recognition. They will begin to close the 30-year knowledge gap, but they will also raise new questions. That is the nature of science. The retrograde rotation of Venus, the specific fact that the Sun rises in the west on the planet closest to Earth, has been known since the early 1960s. After more than 6 decades of knowing this fact, we still do not fully understand why. That enduring mystery is not a failure of science. It is an indicator of how deep the question goes, of how much physics is packed into the single fact that Venus spins the wrong way. Let us now talk about one more dimension of this story, about what Venus's position as the nearest and brightest planet means for its place in human culture and in the long arc of our relationship with the sky. Venus has been known since prehistory. Its brightness makes it unmistakable. Every human culture that has ever observed the sky has known Venus. It is named after the Roman goddess of love and beauty, a name that reflects its brightness and constancy as an evening or morning star. In Mesoamerican astronomy, particularly Mayan, Venus was extensively tracked, and its 584-day synodic cycle was fundamental to their calendar and ritual systems. The Mayans calculated the synodic period of Venus with extraordinary precision. In ancient Mesopotamia, Venus was identified with the goddess Ishtar. The Babylonians tracked Venus systematically and recorded its appearances as morning and evening star on clay tablets. The Venus tablet of Amisaduqa, dated to around 1600 BCE, is one of the earliest surviving astronomical records. For most of human history, Venus was known only as a light, the most reliable and brightest light in the sky after the Moon. Its nature as a planet, its atmospheric composition, its surface conditions, all of this is knowledge of the last few centuries and largely of the last few decades. The retrograde rotation of Venus was unknown to every human civilization that ever lived until 1962. The billions of people across thousands of years who watched Venus as a morning or evening star had no idea that the planet rotates backwards. No observation from Earth alone could have revealed this. The surface is permanently obscured. Radar technology applied to astronomical objects in the early space age revealed a fact about our nearest planetary neighbour that was hidden from all prior human observation, all prior human thought. This is a reminder of how much our understanding of the physical universe has changed in the last few centuries, and specifically in the last few decades. The Venus that Galileo saw phases in, the Venus that appeared in the paintings and poetry and mythology of countless cultures, was a mystery. The planet we understand now, retrograde rotating, sulfuric acid clouds, runaway greenhouse, 465 degrees, no water, no magnetic field, is radically more specific and more strange than anything any prior generation could have imagined. The brightness that made it beautiful to every prior human observer is the same thickness of cloud that hides the extreme surface and drives the possible atmospheric tidal mechanism. The planet, admired for millennia, contains, beneath its brilliant reflective veil, one of the most hostile environments in the solar system, and it spins backward. This is the planet that rises as the evening star, or morning star, depending on the season. This is the planet that Galileo used to prove heliocentrism. This is the planet we are just now beginning to understand well enough to pose the right questions about. Let us talk about something that connects the retrograde rotation of Venus to one of the most practically significant questions in the search for life beyond Earth, about what Venus tells us about the inner edge of the habitable zone and about how we should think about planets orbiting close to their stars. The habitable zone concept, the range of orbital distances from a star where liquid water can exist on a planet's surface, has been refined considerably in recent decades. The outer edge is limited by CO2 condensation at cold temperatures. The inner edge is limited by the onset of a moist or runaway greenhouse. Venus, orbiting at 0.72 astronomical units from the Sun, is currently inside most estimates of the Sun's habitable zone inner edge. The modern conservative estimate places the inner edge at about 0.95 astronomical units from the Sun. Venus is well inside this boundary. But Venus was not always receiving as much solar flux as it does today. The Sun was about 25 to 30% less luminous when the solar system formed 4.6 billion years ago. At that luminosity, Venus at 0.72 astronomical units received roughly the same flux that Earth receives today, enough potentially for liquid surface water. As the Sun has brightened over time, Venus has crossed the habitable zone threshold. If Venus had liquid surface water 3 to 4 billion years ago, it has lost it since. The transition from habitable to hellish is the central unsolved problem in Venus climate history. This has direct relevance for the search for life around other stars. When we search for habitable planets, we look for planets in the current habitable zone. But the habitable zone moves outward as a star ages and brightens. A planet that is currently at the inner edge, like a planet at 0.95 astronomical units around a Sun-like star, may be in the early stages of a transition that Venus underwent billions of years ago. And the rotation rate matters here. Climate models of the inner habitable zone boundary depend critically on the rotation rate of the planet. The habitable zone inner edge for a rapidly rotating planet like Earth is further from the star than for a slowly rotating planet. Rapidly rotating planets form more clouds on the day side that reflect sunlight and extend habitability closer to the star. But slowly rotating planets behave differently. For Venus specifically, the slow retrograde rotation creates an atmospheric circulation pattern that may have made the runaway greenhouse more likely than it would have been if Venus rotated more rapidly. A Venus with Earth-like rotation speed might have maintained habitable conditions for longer or even to the present day. This is why the rotation rate of rocky exoplanets, which we currently cannot measure, is relevant to habitability assessments. When we detect a rocky planet at the inner edge of its star's habitable zone and try to assess whether it is habitable, we are essentially asking which history it follows, the Earth path or the Venus path. And the rotation rate, combined with the atmospheric history, is central to that branching. The Venus analogy for inner edge exoplanets is therefore important. The next generation of telescopes, particularly the Habitable Worlds Observatory concept for NASA, is designed with Venus in mind as a test case. If we can understand why Venus crossed the habitability threshold and Earth did not, we gain predictive power for which exoplanets might be habitable. Let us now talk about the specific physics of the atmospheric tidal torque in more quantitative terms, because the mechanism is elegant and worth understanding in detail. The Sun heats Venus's atmosphere unevenly. The day side receives direct solar heating, the night side does not. This differential heating creates a pressure wave, a thermal tide, that propagates around the planet. The thermal tide is not simply high pressure on the day side and low pressure on the night side. The atmospheric dynamics of Venus, particularly the superrotation which carries heat around faster than the planet rotates, create a more complex pattern. The pressure maximum is not aligned with the subsolar point, the point on Venus's surface directly below the Sun, but is offset, displaced in the direction of the planet's rotation. This offset pressure pattern exerts a torque on the solid planet. A mass distribution, the atmosphere, that is displaced from symmetry relative to the Sun's gravitational pull will experience a net torque. The direction of this torque depends on which way the offset is. For the atmospheric thermal tide on Venus, the theoretical analysis, originally developed by Ingersoll and Dobrovolskis in 1978 and subsequently refined, predicts that the thermal tide creates a retrograde torque on Venus's surface. That is, the atmospheric tide pushes Venus's surface to spin more slowly toward the retrograde direction. Meanwhile, the solar gravitational tide, the direct tidal deformation of Venus's solid body by the Sun's varying gravitational pull across Venus's diameter, tends towards synchronizing Venus's rotation with its orbital period in the prograde direction. This is the same type of tidal force that is slowing Earth's rotation and will eventually tidally lock the Moon. The competition between these two torques, the atmospheric thermal tide pushing retrograde, the gravitational tide pushing prograde, can produce an equilibrium. If the two torques are exactly balanced at some particular retrograde rotation rate, Venus will settle to that rate. The current retrograde rotation of Venus at about 243 days is a candidate for this equilibrium. Whether the actual torques at this rotation rate balance to zero is the question. This depends on the atmospheric structure, the dissipation of tidal energy in Venus's interior, and various parameters that are not precisely known. Recent work using improved atmospheric general circulation models, three-dimensional simulations of Venus's atmospheric dynamics, has made quantitative estimates of the atmospheric thermal tidal torque more reliable. The results suggest that the atmospheric tidal torque is comparable in magnitude to the gravitational tidal torque at Venus's current rotation rate, which is consistent with the current rotation being an equilibrium. But the calculation is sensitive to parameters. The equilibrium rotation rate depends on the mass and structure of Venus's atmosphere, which may have changed over geological time. If Venus's atmosphere was different in the past, less massive or with different compositions and cloud structures, the equilibrium rotation rate would have been different. This raises an interesting possibility. Venus's retrograde rotation may have evolved over time as its atmosphere evolved. Early Venus, with a possibly thinner or water-rich atmosphere, may have had a different rotation rate. As the atmosphere evolved, through volcanic outgassing, through water loss to the runaway greenhouse, the equilibrium rotation rate changed. The current 243-day retrograde period is the result of this long evolution. This scenario connects the atmospheric evolution and the rotation evolution into a single coupled history. Understanding one requires understanding the other. Let us now talk about one more specific aspect of Venus that is directly relevant to understanding its rotation, the internal structure and its possible differences from Earth. Earth's interior is layered, a solid inner core of iron-nickel at about 5,150 to 6,370 kilometers depth, surrounded by a liquid outer core of liquid iron and nickel from 2,890 to 5,150 kilometers depth, surrounded by the mantle from 35 to 2,890 kilometers depth, and the crust from 0 to about 35 kilometers depth. The liquid outer core is responsible for Earth's geodynamo, the generation of Earth's magnetic field through convective motion of conducting liquid iron. The driving force for this convection includes heat flow from the inner core, chemical buoyancy from the crystallization of the inner core, which releases lighter elements into the liquid, and possibly primordial heat left over from Earth's formation. Venus's interior is unknown in detail. We have no seismological data. We have only remote sensing and theoretical inference. The bulk composition of Venus, inferred from its density and from analogy with Earth, suggests it probably has a similar layered structure. A core of iron and nickel, a silicate mantle, a thin crust. But whether Venus currently has a liquid outer core, and whether that liquid core is convecting, are unknown. The absence of an intrinsic magnetic field places constraints. Either Venus's core is not convecting vigorously enough to generate a dynamo, or Venus does not have a liquid outer core, or Venus's core is convecting, but in a geometry that does not produce a dipolar magnetic field. All three possibilities exist and are debated. One hypothesis: Venus's core has solidified completely, or nearly so, and the absence of a liquid conducting layer means no geodynamo. But simple cooling models suggest that Venus's core should still be at least partially liquid, given that it has similar size and composition to Earth's core and has been cooling for about the same 4.6 billion years. Another hypothesis: Venus's core is liquid but is not convecting. For convection to occur in a liquid core, heat must flow from the interior to the exterior fast enough to overcome the adiabatic lapse rate in the core. If Venus's mantle is hot enough, if the mantle itself is not efficiently cooling the core, then the core may be thermally stratified without convection. Venus's lack of plate tectonics may be relevant here. On Earth, plate tectonics efficiently cools the mantle, which in turn cools the core and drives core convection. On Venus, without Earth-like tectonics, the mantle may cool more slowly, the core cools more slowly, and convection may be suppressed. This last hypothesis connects three of Venus's anomalies: the lack of plate tectonics, the lack of a magnetic field, and the possibly stagnant core. All three may be manifestations of the same underlying thermal evolution. The slow rotation of Venus connects to this through two possible mechanisms. First, slow rotation reduces the Coriolis effect in the core, making organized convective flows, the kind needed for dynamo action, less efficient. A more rapidly rotating Venus might have a stronger dynamo. Second, as mentioned, the slow rotation produces a different atmospheric circulation, which leads to different surface heat flux patterns, which potentially affects the mantle cooling rate and therefore the core dynamics. These connections are speculative in their details, but physically motivated. They illustrate how deeply Venus's rotation is entangled with its other properties. The rotation is not just an isolated anomaly, but a property connected to the core dynamics, the mantle evolution, the surface tectonics, and the atmospheric dynamics simultaneously. Understanding why Venus has no magnetic field requires understanding its interior evolution. Understanding its interior evolution requires understanding its thermal history. Understanding its thermal history requires understanding its atmospheric evolution. Understanding its atmospheric evolution is connected to understanding its rotation. Everything in Venus science connects to everything else. Let us now talk about what might be the most scientifically valuable near-term step for understanding Venus's rotation, a step that could be taken with existing ground-based telescope facilities before any new space missions arrive. The key unknown in the atmospheric tidal hypothesis for Venus's rotation is the magnitude and direction of the atmospheric thermal tidal torque as a function of Venus's rotation rate. The current torque at the current rotation rate can be estimated from atmospheric models, but what the torque would be at different rotation rates and how the equilibrium rotation rate changes with atmospheric conditions requires more sophisticated simulations. Improvements in Venus General Circulation Models, GCMs, have been rapid in recent years. Groups at NASA Goddard Institute for Space Studies, at the Laboratoire de Météorologie Dynamique in Paris, at the University of Oxford, and elsewhere, have developed increasingly realistic three-dimensional simulations of Venus's atmospheric circulation. These models have achieved the atmospheric superrotation in simulations. For years, the superrotation was difficult to reproduce from first principles, and are now able to simulate the wave phenomena observed by Akatsuki. As these models improve, their predictions of the tidal torque become more reliable. The critical test would be to run these models at different rotation rates, faster and slower than the current Venus rotation, and calculate the equilibrium rotation rate where the atmospheric and gravitational tidal torques balance. If the predicted equilibrium matches the observed rotation rate of 243 days to within uncertainties, that would be strong evidence that the atmospheric tidal mechanism is correct. Conversely, if the models consistently predict an equilibrium rate that does not match, if the balance point is at a different rotation rate, regardless of how the models are configured, that would push toward the impact hypothesis or other explanations. This kind of model comparison is ongoing. It does not require new missions. It requires computing power and improved physical parameterizations. Progress in Venus GCM development is one of the most active areas in Venus science right now. Ground-based observations can also contribute to constraining the atmospheric dynamics. The Atacama Large Millimeter Array, ALMA, can observe Venus in the millimeter and sub-millimeter wavelength range, detecting spectral lines from atmospheric molecules and measuring winds through Doppler shifts at different altitudes. Recent ALMA observations have detected the wind field in Venus's lower atmosphere with unprecedented detail, filling in the altitude range between the cloud tops that are well characterized and the surface that is accessed by entry probes. The James Webb Space Telescope can observe Venus in the near-infrared windows, where the thick atmosphere becomes partially transparent, and radiation from the lower atmosphere and surface can escape. These observations constrain the temperature profile and chemistry of the lower atmosphere and have already been used for calibration purposes. As JWST continues to observe Venus, the data will constrain the lower atmospheric dynamics that are important for the tidal coupling. All of this ground-based and space telescope work is preparing the scientific ground for the Da Vinci, Envision, and potentially Veritas missions. The more we understand about the current state of Venus's atmosphere, the better we can interpret the new data these missions will return. Let us now talk about one final aspect of the Venus rotation story that deserves attention, about what the question of Venus's retrograde rotation means for how we think about the arrow of time and the irreversibility of planetary histories. The formation of the solar system was a process that involved enormous amounts of stochasticity. The specific impacts that occurred, the specific timing of gravitational interactions between growing planetary embryos, the specific trajectory of any given planetesimal. All of these were in principle determined by initial conditions, but are in practice unpredictable in their specific details. If you could run the formation of the solar system again from the same initial conditions, the same molecular cloud, the same distribution of matter and angular momentum, would you get the same 4 rocky planets with the same rotation states? Almost certainly not. The chaotic nature of the n-body problem that describes the interactions of many gravitating bodies means that small differences in initial conditions produce large differences in final outcomes. Run the solar system formation 1,000 times and you would likely get 1,000 different outcomes for the rotation of the rocky planets. Venus's retrograde rotation is therefore, in some sense, a product of contingency, of the particular path that this particular solar system happened to take. In some other realization of this solar system's history, Venus might have had a prograde rotation and might have remained habitable. Or Earth might have experienced the anomalous impact and ended up with a retrograde rotation and a runaway greenhouse. This contingency is philosophically significant. It means there is no deep reason why Venus spins backwards that we will eventually discover, no necessary physical law that mandates this outcome. The answer to why does Venus spin in the opposite direction may ultimately be because a particular sequence of events happened to occur, and these events were the result of the particular initial conditions and the particular trajectory through phase space that this solar system happened to follow. This is not a satisfying answer in the sense of reducing the phenomenon to a fundamental law, but it may be the true answer. And recognizing this teaches us something important, that the specific configuration of a planetary system is not the inevitable outcome of physical laws acting on initial conditions. It is one of many possible outcomes, selected by the particular history that happened. This means that when we observe other planetary systems around other stars, through the Kepler data, through radial velocity surveys, through direct imaging, we should not expect to see copies of our solar system. We should expect enormous diversity. And indeed, we observe this diversity. Hot Jupiters, super-Earths, tidally locked planets, retrograde planets, systems with entirely different architectures from our own. Venus's retrograde rotation is one specific instance of the diversity of outcomes that contingent planetary formation produces. Understanding it in all its specific physical detail is part of understanding how the range of outcomes is determined. what processes are deterministic and what are stochastic, and ultimately what this means for the prevalence and diversity of habitable planets throughout the galaxy. The planet that rises in the west is not just an anomaly. It is a window into the nature of planetary formation and evolution as stochastic, contingent, irreversible processes unfolding over billions of years. Let us now talk about what the near future holds for Venus science, about what we might expect to learn in the next decade and a half from the combination of Akatsuki, Da Vinci, and Envision. Akatsuki continues to operate in orbit around Venus. As of 2024, it has been in operation for about 9 years. It was originally designed for a 2-year science mission. Its extended mission continues to provide valuable data on Venus's atmospheric dynamics, cloud morphology, and thermal structure. It is aging and some instruments have degraded, but its cameras continue to provide monitoring of the atmospheric superrotation and cloud patterns. Key questions Akatsuki is still addressing include: how does the superrotation vary over time? Are there long-period oscillations in the circulation pattern? How do the stationary wave features correlate with surface topography? What is the day-night temperature contrast in the lower atmosphere? Da Vinci, currently in development for launch in the late 2020s, will provide the first in-situ atmospheric chemistry measurements below the cloud base since the Soviet Venera and Vega missions of the 1980s. Its descent probe will measure the noble gas abundances that tell us about Venus's origin and volatile history. If Venus had liquid water early in its history, the xenon and argon isotopic ratios in its atmosphere should reflect this. The probe's measurements could reveal whether Venus was ever wet. Da Vinci will also take high-resolution images of Aphrodite Terra, one of the largest highland regions on Venus, during its approach and descent. These images may reveal whether the highlands are composed of granite-like rocks that form in the presence of water, as Earth's continents are, or of volcanic basalts, which do not require water. This distinction would be direct evidence about Venus's water history. Envision, currently in development for launch in the early 2030s and arrival at Venus in the late 2030s, will orbit Venus for at least 4 years, conducting comprehensive science. Its radar will map the surface at better resolution than Magellan. Its subsurface sounder will probe the upper few hundred meters of Venus's crust. Its spectrometers will measure surface and atmospheric chemistry. Its radio science experiment will measure Venus's rotation period with unprecedented precision. The combination of these missions, Akatsuki's long-term atmospheric monitoring, Da Vinci's atmospheric chemistry, Envision's comprehensive surface and atmospheric characterization, represents a turning point in Venus science. By the mid-2040s, we will likely have enough data to definitively test whether the atmospheric tidal hypothesis is correct, to characterize Venus's geological activity, to constrain whether Venus was ever wet, and to precisely measure whether Venus's rotation period varies. The question, why does Venus spin in the opposite direction, will not be definitively answered by any single mission or any single observation, but the combination of observations that these missions provide will narrow the possibilities dramatically. The answer that emerges from this program of missions will be one of the more important results in planetary science in the coming decades. Not because Venus's rotation is intrinsically of great importance, but because of what it tells us about the range of evolutionary paths available to Earth-sized planets, about the role of rotation in climate and habitability, and about the contingency and diversity of planetary outcomes around Sun-like stars. Venus rotates backwards. We have known this for 60 years. In another decade or two, we may finally understand why. Go outside tonight. Look west after sunset, or east before sunrise, depending on where Venus currently is in its apparition. Find the brightest point of light in the sky that isn't the moon. It will be unmistakable. No star comes close to its brightness. That is Venus. Hold it in your field of view for a moment. That light you are seeing left Venus about 2 minutes ago. It traveled 100 to 250 million kilometers, depending on the current geometry, to reach your eye. It was reflected from clouds of sulfuric acid hanging 45 to 70 kilometers above a surface you can never see from Earth. Beneath those clouds, right now, as you look, the surface is 465 degrees Celsius, hot enough to melt lead. The pressure is 92 times Earth's atmospheric pressure. The sky is permanently overcast with sulfuric acid. The Sun, when it crosses Venus's sky, moves from west to east. The Sun rises in the west on Venus. The planet closest to Earth, the brightest object in the night sky, the planet named for the goddess of beauty, and its sun rises in the wrong direction. Why? We do not know with certainty. We have been asking the question for 60 years, since radar measurements first revealed the retrograde rotation in the early 1960s. We have hypotheses. A large impact early in the planet's history flipped its axis. Solar tidal forces and the thermal tides of its massive atmosphere drove it from prograde to retrograde over billions of years. Some combination of both, perhaps something else entirely. What we know is this: Venus and Earth formed from the same disk of material around the same star at roughly the same time. They are nearly twins in size and mass, and they are complete opposites in almost every way that matters for habitability. Venus is 465 degrees. Earth is 15 degrees. Venus has 92 atmospheres of pressure. Earth has 1. Venus has no liquid water. Earth is covered in it. Venus has no magnetic field. Earth's magnetic field shelters life from the solar wind. Venus has no plate tectonics in Earth's form. Earth's tectonic recycling regulates the climate. Venus has no life. Earth has billions of species. The retrograde rotation is connected to many of these differences. The slow rotation may suppress the geodynamo and therefore the magnetic field. The atmospheric dynamics driven by the slow rotation may have contributed to the runaway greenhouse that eliminated Venus's water. The rotation history is tangled with the impact history, the atmospheric history, the volcanic history, the water history, all of it interwoven. Understanding why Venus rotates backwards is part of understanding why Venus is not Earth. And understanding why Venus is not Earth is part of understanding how rare or common Earth-like conditions are in the galaxy. If we knew precisely what sequence of events made Venus what it is, whether it was inevitable given its position, or whether it depended on specific contingent events that might just as easily have gone differently, we would know something fundamental about the probability of habitable planets. 3 new missions are on their way or in development. Da Vinci will descend through Venus's atmosphere and measure its chemistry with unprecedented precision. Envision will orbit Venus for years and map its surface and monitor its atmosphere. Perhaps Veritas will eventually follow with even more detailed surface mapping. By the 2040s, we will know much more about Venus than we know now. We will know whether its atmosphere contains the isotopic signatures of an ancient ocean. We will know whether its surface is currently volcanically active. We will know whether its rotation period varies and on what timescale. We will have the data to test whether the atmospheric tidal mechanism can explain the retrograde rotation quantitatively. The answer, when it comes, will not just be about Venus. It will be about how planets work as coupled systems, how rotation, atmosphere, geology and chemistry interact over billions of years to produce wildly different outcomes from similar starting conditions. Right now, tonight, Venus is the evening star, or the morning star depending on the season. It has been both throughout human history. Every culture that has ever looked at the sky has seen it and named it and given it significance. The Babylonians tracked it on clay tablets 3,600 years ago. Galileo used it to prove heliocentrism in 1610. We sent spacecraft to its surface in the 1970s and 1980s and survived, barely, briefly, in the most hostile planetary environment in the inner solar system. And we still do not know why it spins the wrong way. Look at that bright point in the west one more time. Beneath the brilliant veil, in the orange dim light of its surface, in the dense hot acid atmosphere, in the geologically active basaltic plains, there is a world-sized mystery. A planet our size, our neighbour, our twin in so many measurements, spinning backwards, still not fully understood, still asking the question.